Hello, everyone. It's my great pleasure to introduce today's speaker, Yizheng. So Yizheng is a PhD student from Brown University. And I think before Brown, Yizheng was a master's student here, working in our group with Professor Vasia and John. So I think today, this work, it's part of the presentation will appear SDI next year. And Yizheng's research interest in the distributed system, microservices, and serverless computing. So yeah.
Thank you for the introduction. Hi, everybody. Today, I'm really happy to be back here and talk about my recent work around performance optimization for service-oriented architecture. So feel free to interrupt me anytime if you have any questions. So first of all, what is service-oriented architecture? Instead of bundling all functionalities into one large monolithic applications, this architecture decomposes applications into independent and reusable services. Service here is designed around a specific capability, for example, authentication or caching. And all of them communicate with each other through some standardized protocols. This architecture originates from early enterprise concept of service integration in web applications. And it continues to influence today's software system designs, especially in cloud environments and big data systems. For example, specialized middleware for message delivery and modern paradigms such as microservices and serverless platforms. One of the most representative and widely used evolutions is microservice architecture, which applies the same service-oriented principle in developing large-scale distributed applications. Companies such as Amazon, Netflix, and Meta heavily use microservices in production. Let's take Uber as a concrete example. This is a dependency graph of all services to support the Uber application. Reported in 2019, it has already consisted of thousands of microservices and applying thousands of commits per day to update these services. This popularity largely comes from the flexibility of microservices, where different teams can develop and deploy services independently, improving the scalability and fault tolerance of the whole application. However, this flexibility comes at a price. Managing thousands of loosely coupled services introduces significant complexity, high operational costs, and challenges in debugging performance issues. As a result, even large companies have started rethinking this architecture and already moved some microservices back to monolithic applications. In today's talk, I'm going to focus on minimizing the complexity in the context of performance optimizations for these services. The first and the major part of the talk is Slowpoke, which is to appear at NSDI 26, takes a high-level view across all services to help developers plan their optimizations more effectively by performance prediction. The second part of the talk, which was presented at PROS 25, dives deeper into the execution of an individual service. It proposes a provocative idea that rethinks how a service can schedule its internal work efficiently. At the end of the talk, I will also briefly mention some other lines of work that I'm involved toward automated performance optimizations. Before I move on, any questions about the context and plan for today? All right, let's jump into the first system, Slowpoke, which is joint work with John and Vasia here at BU. The throughput of microservices matters for cost efficiency, scalability, and quality of service delivery. For example, a shopping platform such as an online boutique application must handle traffic increases when planning market expansion. To improve the throughput of microservices, developers often need to decide where to spend these optimization efforts. In the topology of the online boutique application, there are many different options. For example, developers can improve the cart lookups by implementing a better in-memory key value store, speed up the recommendation queries by caching per user information, or one of many others. Correctly deciding where to spend the optimization efforts is crucial for maximizing benefit while minimizing engineering efforts and financial cost. To make the correct decision, developers need to evaluate these options by predicting the performance benefit. For example, what throughput the application can sustain if I optimize the car service from 10,000 requests per second to 20,000 requests per second. However, answering this question is challenging using existing approaches. For example, distributed tracing captures complex service dependency and total time each request spent on each service. However, optimizing a service may hit the bottleneck induced by, for example, a mutex log in another service, which cannot be observed in tracing information because it does not have the knowledge of service internals. On the other hand, profiling each service in isolation requires replaying the requests and responses to the service at a high rate to stress test the service, which is not scalable due to exhaustive resource consumption. To answer the question, we introduced Slowpoke, a system that accurately quantifies the effect of hypothetical optimizations on end-to-end throughput for microservice applications, without relying on a prior knowledge of service internals or the execution graphs. So to apply Slowpoke, developers need to provide 3 inputs. First, a target service. Second, a hypothetical optimization applied to the target service. Slowpoke is agnostic to an actual optimization implementation. So the optimization here can be expressed in reduction in average processing time or improvement in service capacity. For example, reducing the processing time per request of the target service by 50%. And third, a predefined workload. Given microservices that use communication libraries provided by Slowpoke in Go, Slowpoke predicts the end-to-end throughput as if the optimization was implemented. In the online booting example, Slowpoke can tell that optimizing the cross service by 50% can improve the throughput from 3,900 requests per second to 6,800 requests per second under a mixture of a various type of requests. Developers can also use Slowpoke to learn the end-to-end throughput curve followed by the target service optimization, which tells when optimizing the target service yields no further benefits. At a high level, Slowpoke conducts 2 experiments. First, it prevents the workload to collect information, to collect per service information. Second, it slows down all non-target services. And the throughput measured in the slowdown execution will be used by Slowpoke to predict the throughput improvement based on the performance model. Before I get into details of the system design and different components and how the model works for Slowpoke, is there any question about the problem and the input-output of the system? Sure.
For the hypothetical optimization, you mean the input developer needs to provide the internal logic, or do I acquire a log or some other contained resource?
That's a good question. So this input here does not require any implementation detail. You can only tell Slowpoke, well, if I can optimize the service by 50%, no matter how you actually optimize it, you just need to know if I can do it, what's the benefit I can get?
Benefit for this one service?
No, the whole application.
The whole application.
Because the benefit for this service will be 50%. That's the hypothetical optimization. That makes sense?
Yeah.
Any other questions?
Is the optimization just defined by the latency, or actually it can be, let's say, by 50%, it can be the throughput for a certain service increased by 50%?
Basically, it can be anything, as long as you can improve the throughput of the service. For example, you can reduce the processing time, which also reduce the latency. But as long as you can improve the service, you can give input to the system.
For your system, you need to run the workload.
Yes.
What if I change the workload? In real world system, you have different types of workload. Is this output still valid? Or
I would say the assumption here is we need to target a predefined workload, because if the workload change, the entire call graph might change, and optimizing a service
in cloud system, the workloads frequently change.
Yeah, but you can first like pre-profile the workload of the system in production to see like what's the percentage of this kind of workload or that workload. And you can just do this optimization for this particular workload. Right. Now let's first talk about the system design and different components of Slowpoke. In a common microservice deployment, each service runs in a pod and managed by Kubernetes and communicates with each other through some layer 7 protocols such as HTTP or gRPC. Slowpoke first introduced lightweight instrumentation to these libraries to monitor traffic information without affecting the service interactions. Slowpoke also introduced a control process called poker, running alongside each service within the same pod. Each poker collects information from the instrumental library through a standard Unix pipe and communicates with its neighboring poker through dedicated TCP channels. The coordinator runs on the control plane to conduct experiments. In the profiling experiment, each poker collects per service information, including the number of CPUs, its directly connected services as neighbors, and the traffic load. All this information will be used by the model to calculate the slowdown for all non-target services. During the slowdown experiment, the coordinator dispatches this calculated slowdown information to all pokers running alongside non-target services. The poker running alongside the target service will initiate the slowdown process by sending control messages to its neighboring pokers. Upon receiving this message, each poker further propagates this message to its neighboring poker, similar to a gossip protocol, and then passes the service by sending a 6 stop to the whole service process group for a certain duration. And the throughput measured in this slowdown experiment will be used by the model to predict the throughput improvement. The idea of the model is that the impact of any hypothetical optimization can be estimated by simulating the effect of speeding up the target service, that is, slowing down all the target services. Let me use a simplified example of 3 single-threaded services to illustrate the key idea here. So here, service A accepts the user request, processes for 1 time unit, and then calls B, which in turn processes for 3 time unit and calls C. Upon completion of all this internal processing, the user receives a response. When the whole application is saturated, the throughput will be 1 request per 3 time units, dominated by service B, which has the longest processing time. Assuming we would like to optimize the service B by 2 time units, after optimization, the throughput will be improved to 1 request per 2 time units. And the delta here, basically the amount of time being optimized. Instead of directly optimizing service speed, which takes time and effort, we slow down all non-target services A and C by the same amount, which is 2 time units here. In the slowdown execution, the throughput will be 1 request per 4 time units, dominated by C, which has the longest processing time here. And intuition of the model is what we call bottleneck equivalent, that the slowdown execution will be bottlenecked by the same service as the optimized execution. In this case, we can establish a mathematical model to infer the throughput after optimization by using the slowdown execution and the delta, which is the optimization effects. Using this formula does not require understanding the service internals and the execution graphs to predict the throughput. We generalize the model. By based on a mathematical formulation using linear programming. The model relies on a key constraint that for each service, the throughput multiplied by the average consumption per request for a particular resource must not exceed the quota for that resource. For example, the average consumption per request can be CPU time per CPU resources. And the optimization here is actually the process of maximizing the end-to-end throughput by reducing the average consumption per request for the target service while still satisfying all these constraints. For example, reducing the CPU time by the amount of D for the target service. In contrast, the slowdown represents the opposite case where the target service consumes as usual, but all other services increase the consumption by a certain amount d prime. By carefully configuring d prime based on the value of d and other factors, these two linear programs are equivalent. Just to be clear, the equivalence here does not mean that these two linear programs have the same solution. Instead, they have the same constraint that gives the solution to each linear program. In other words, if constraint K takes the equality in the linear program for optimization, it will also take the equality in the linear program for slowdown execution. Based on this mathematical formulation, we generalize the model to support more realistic and complex scenarios such as multi-threaded services, dynamic call graphs, and different types of bottlenecks, for example, the mutex-induced ones. The performance model provides a theoretical modeling or throughput prediction. However, its effectiveness depends on the actual slowdown mechanism. First of all, to reduce the overhead of pausing the service every incoming request, Slowpoke uses a batching to pause the service upon receiving a predefined number of requests. Given the complex microservice dependency, how to coordinate this process across the entire microservice graph also matters. Let's bring back our previous example to showcase why this matters. In this case, service B is the target service. In the naive coordination, each poker running alongside non-target services independently pauses the service upon receiving 3 incoming requests. In this case, poker A pauses first, which stops service A from processing the 3rd request. As a result, poker C can only pause after service A resumes and finish processing the 3rd request. The serialized pausing here incurs higher average latency, which requires more in-flight requests with the number of services to avoid throughput degradation. This also leads to more resource consumption due to more queuing and possibly more open connections, which may distort the accuracy in prediction. Slowpoke uses the following mechanism to coordinate pauses across the entire microservice graph. The poker running alongside the target service initiated the process by sending TCP messages to its neighboring pokers. Upon receiving this message, each poker further propagates the message and then pauses the service almost at the same time. In this case, the latency introduced by the slowdown will not increase with the number of services in the application, which avoid throughput degradation and the inaccuracy in prediction. Before I move on to the results, is there any questions about all the technical details about Slowpoke? All right. In the evaluation, we focus on one key question: how accurate Slowpoke throughput prediction is. To evaluate Slowpoke, we use 4 realistic applications from desktop benchmarks and Google demo application. To generate ground truth after optimization, we use a combination of artificial deceleration by spinning and also realistic scaling. We also evaluate Slowpoke across a diverse range of microservice characteristics using more than 100 synthetic benchmarks generated by Yizheng, a microservice benchmark generator. All these benchmarks come from 9 topologies and 3 variations in configuration, including communication protocols, request concurrency, and target service position. We extend Yizheng to support dynamic call graphs where the actual path of a request depends on the state of the system or the input. For example, in topology 9, the root service will call one of the downstream services only in 20% of the request, simulating calls to database services when cache miss happens. We report the error as the relative difference between prediction and the ground truth. Let's first take a look at the results across 4 realistic applications. The x-axis here is the optimization percentage by removing the artificial spinning time, where 50% means reducing the total processing time per request for the target service by 50%. And the y-axis here is the raw end-to-end throughput. Blue curves here represent the predicted throughput by Slowpoke. And what's the reality? The black curves here represent the ground truth after applying actual optimizations. We can see that the prediction actually aligns with the ground truth. And the actual root mean square error here is 2.1% across all the benchmarks applications. We can, in general, Slowpoke can accurately predict the throughput improvement for diverse applications, no matter optimizing the target service yields significant benefit or not. In previous experiments, we conduct the actual optimization by removing the artificial spinning time. We're also interested in seeing if Slowpoke can actually handle realistic optimizations, such as scaling. So we first scale out the target surface in the online boutique benchmark from 1 replica to 2 replicas by adding another instance to run the same service. We also scale up the target surface in social media benchmark by from 2 virtual CPUs to 4 virtual CPUs by directly changing the type of machines. And the errors here are comparable to previous experiments, demonstrating that Slowpoke can also handle realistic optimizations. For synthetic benchmarks, with 1,080 experiments in total, we group all the data points based on different characteristics. The x-axis here is represent different characteristics, including topologies, communication protocols, and, for example, whether the target service is an existing bottleneck. And the y-axis here is the raw error percentage. We can see that Slowpoke does not introduce significant difference across diverse characteristics. And it achieves a root mean square error of 1.9% across all the benchmarks. The highest error occurs in a topology with multiple dynamic paths at 90% optimization percentage. The 90% optimization percentage results in an unrealistic fast service, which amplify the overhead of Slowpoke and lead to a higher underestimation. Before I move on to the second part of the talk, is there any question about the evaluation results and also the Slowpoke in general? All right. As I mentioned earlier, Slowpoke provides a high-level view that helps developers identify where optimization efforts provides greatest improvement. However, to actually carry out those optimizations, developers need to dive deeper into individual services, open the box to understand what's happening inside, and propose targeted optimizations. One such example can be related to how a service schedules its internal events. The second idea I'm going to talk about is a hybrid scheduler that combines the benefit of cooperative and preemptive scheduling. Services are typically written in various programming languages. To handle high incoming traffic from the users and other services, each service relies on the language runtime or the underlying operating system to schedule its internal work efficiently. To start with, let me give you a bit of background on 2 classic scheduling approaches. Preemptive scheduling is widely adopted in general purpose operating systems, and it is common in thread-based programming models. The scheduler can interrupt a task at any time and switch to another. For example, after task A runs for a while, the scheduler can preempt task A and switch to task B. This often ensures fairness and liveness. For example, the Linux completely fast scheduler can fairly share the CPU time and prevent any single task from monopolizing the execution. However, preemptive scheduling complicates the shared state management. For example, when preemption happens between 2 tasks updating the same variable, the second task may use a stale value to corrupt the shared state, introducing a concurrency bug. Such bugs can result in disasters in the real world, for example, affecting the Medicare machines or even the Pathfinder on Mars. Therefore, synchronization mechanisms such as locks or atomic operations are required, but burdensome for both programming and reason. In contrast, Cooperative scheduling provides direct scheduling control. Instead of being preemptive, a task either runs to completion or voluntarily gives up the control by using yield or calling an asynchronous operation and waiting for its completion. Because task switches are explicitly defined and often controlled by the developer, cooperative scheduling simplifies the shared state management and often provides higher efficiency. Cooperative scheduling is widely used in various programming languages, event-driven runtimes, and even some real-time operating systems. However, if a task never used the control, either accidentally by a tight loop or intentionally by denial of service attack, they can monopolize the execution and exhaust the resources. This actually affects a large scale of real-world software and systems. For example, freezing the gaming engine, the Go language runtime, resulting in outage in Stack Overflow, and CPU exhaustion in Cloudflare. Now, let's focus on the problem in cooperative runtime using a concrete example. Here, we have a service in JavaScript serving requests for regular expression matching. The pattern tries to find one or more letters of A followed by a letter of B. However, this pattern is vulnerable to catastrophic backtracking. If an attacker sends a long string of letters A without terminating B, the regular expression engine can spend exponential time finding all possible partitions. Because JavaScript runtime such as Node.js relies on each task to voluntarily give up the control before scheduling the next one. In this case, a single malicious input can basically tie up the entire server almost forever. This actually affects more than 10,000 NPM packages reported in 2018. There is some effective approach to mitigate this specific denial of service attack. For example, enforcing a linear time regular expression engine or guarding the matching process in worker threads with strict timeouts. However, these solutions are not generalizable to other forms of misbehaving execution because they do not have a mechanism to enable preemption in a cooperative environment. More general ideas include introducing limited preemption using compiler instrumentation to yield the control more frequently. However, the feasibility of instrumentation depends on the actual code path. For example, instrumenting a tight loop may incur much higher overhead. And they also lack the flexibility as fine-grained preemption may introduce unnecessary yielding points, whereas coarse-grained preemption may fail to mitigate the problem effectively. Any question about this example?
Yizheng, I have a general question about the previous slide.
Mhm.
Where you saw the problem with preemptive scheduling. Yeah, so here, okay, I understand why there can be concurrency lag.
Mhm.
But since the Linux first scheduler does preemption,
Mhm.
then how is this problem solved in practice? How do we avoid this case in practice?
I think you can use like a lock or something to prevent the scheduler schedule another task before this task release the lock or finish the execution.
Okay, so you rely on the fact that the program is written correctly so that this doesn't happen.
Yeah. So this doesn't happen in cooperative scheduling because each task runs to completion. But this happens in preemptive scheduling. Therefore, we require developers to write correct programs using synchronization methods.
Okay.
Yeah. All right. To solve the problem, we propose a hybrid scheduler that allows only carefully controlled and developer configurable preemption in an otherwise cooperative environment. In other words, we start with a fully cooperative environment and we introduce constrained but safe preemption. The hybrid scheduler preserves the cooperative abstraction that each task runs to completion or voluntarily used to control. It allows control and configurable preemption only when necessary, for example, for fairness and liveness. This hybrid scheduler provides safety guarantee as the preemption is not allowed to modify the shared state arbitrarily. It also provides flexibility that allows developers to define whether and when the preemption happens and what task the preemption can execute. For example, the preemption can be triggered periodically to time out a long-running execution or prioritize handling health checking requests when it actually arrives. Now let's bring back this example to see how the hybrid scheduler can mitigate the problem here. To use the hybrid scheduler, developers simply import a library and define a preemption policy that instructs the runtime to trigger the preemption every 50 milliseconds, for example. Developers also need to define an action that will be executed in the preemption. The action here actually checks if the execution time of the regular expression handler runs longer than 100 milliseconds. If that's the case, the runtime can abort the execution. Otherwise, it can just continue the handling of the regular expression normally without doing anything. More importantly, this preemption policy and action and allow the runtime to schedule its original work fully cooperatively and seamless. All right. The hybrid scheduler is designed as an extension to a general cooperative runtime. Developers write codes that run cooperatively in the same way as before. For example, in an execution context provided by the Lua runtime or the V8 JavaScript engine in Node.js. The hybrid scheduler provides another abstraction layer that allows developers to define what task the preemption performs and under what conditions. At runtime, the hybrid scheduler first separates the execution into two isolated contexts, the original main execution context and a new preemption execution context. The hybrid scheduler will run all the preemption-related actions and executions entirely and completely in the preemption context without affecting the main context. By using dedicated state and control stops provided by the runtime, the preemption can perform control operations to affect the execution of the main execution piece. For example, throwing an exception to abort the execution in the main context. How does the preemption actually get triggered? The hybrid runtime uses a interrupt handler that preempt the main execution context and switches to the preemption context. The handler is invoked by either timers or incoming events. To provide flexibility, it requires extending the underlying event loop, such as libuv in Node.js, to be able to preempt at event granularity. For performance, it requires using a more efficient notification mechanism, such as using user interrupt over a transition of a slow operating system signal. In previous example, we showed that the action in the preemption is expressed in a very limited language that either continues or aborts the execution. However, as a developer, you definitely want to perform many other actions. For example, maintaining some states or accessing runtime information such as event queues to make some decisions. The hybrid runtime expands this limited language to a subset of the source language but preserves some key invariants for safety guarantee. For example, the preemption must terminate. It is not allowed to import any third-party libraries or modify the application states arbitrarily. Additionally, the hybrid runtime introduce a static checker to verify this invariant before applying the preemption action at runtime. If one of the actions violates some of the invariants, the static checker will reject the preemption and provide error messages to the developer to refine their actions. If we succeed in realizing all these designs, we envision that the hybrid scheduling approach could be applied to broader classes of problems in diverse services. For example, it can improve the performance by preventing header-line blocking in high-performance services, such as database. It can also provide stronger security guarantee by preventing asymmetric denial of service attack in web applications. It can also support program instrumentation and profiling to better characterize the performance of services. By combining Slowpoke and a hybrid scheduler, developers can perform guided optimizations, not only in complex microservices, but also in general service-oriented architectures by adapting these approaches to reason about and apply actual optimizations. However, to truly enable automated optimizations, we need to move beyond manual reasoning and optimizations. Under this vision, I am involved in other license work, for example, automatically transforming monolithic applications to microservices and vice versa, depending on the efficiency considerations. And I also work on scaling out daily programs such as shell scripts to serverless computing and accelerating the incremental development of these daily programs, both automatically and correctly. Together, this direction aims to get closer to increasingly automated and adapted service-oriented architectures. In conclusion, this talk covers two projects, one for performance prediction, another for actual optimization through a hybrid scheduler. I've been fortunate to work with a group of talented people on these two projects. And more papers and ongoing research are available on my website and also the website of the Atlas Research Group at Brown. Feel free to check them out. And finally, I will be around throughout the day, and I would love to chat, not only to get feedback on my research, but also to learn some exciting work happening here at BU. All right, thank you, and I'm happy to take more questions.
So for the second paper, I didn't really understand how did your scheduler solve the problem?
Maybe a little bit more specific.
Because you rely on the programmer to specify what he wants to carry out during the preemption, right?
Right.
And your initial problem was that you were relying on the programmer to write accurate software. So how did that address the problem?
I think the preemption in this case, in the hybrid scheduler, is really limited. So it's only defined only when necessary, when you are trying to solve some problems, for example, fairness or liveness. The preemption is not allowed to do arbitrary things as in the fully preemptive scheduling case. And we also enforce some static checker to enforce some invariance to make the preemption safe.
So where is this preemption? Where does it happen in the JavaScript engine you said?
Yeah, the JavaScript engine. Like after the developer define this preemption policy, the JavaScript engine will periodically trigger the preemption, for example, every 15 milliseconds, no matter what the code is currently executing. And then after, like inside the preemption, the scheduler or the runtime will actually execute the action, such as the monitor function.
But before this, you were talking about the Linux scheduler.
Mm-hmm.
So that happens in the kernel. While
yeah, that's the
JavaScript
kernel
engine
level.
is
This
in
is the
user
language
space.
runtime.
So the JavaScript engine itself would get preempted by the kernel, right?
Yeah, that's another thing. So basically, when you get
So I don't understand the comparison between the two.
Oh yeah, sure. So when you get preempted by the kernel, it's at the kernel level and across like different applications, right? And then when they switch back to your application, you resume all the states you have. So you continue executing what you're executing before.
Yes.
Right? So there's no problem in this environment because when you switch back, you have all the things as before. There's no like a database here.
So what was the problem in the first place?
Oh, the first, you mean the preemptive scheduling?
Yes.
So when you do like concurrent execution, you have multiple threads to handle different requests, right? And you are kind of accessing the shared state. But here, when you have concurrent requests, it's still in a cooperative way. Like you first finish the first request and then second request.
So this is scheduler that you're talking about is not the Linux scheduler.
It's not the Linux scheduler, the language runtime scheduler.
Okay.
So this scheduler, it just supports one application at a time, right?
Right. That's basically when you run the JavaScript application. There's a runtime supports that. And you run another application, there's also the same runtime there to handle that application.
So at the same time, it is supporting only one application, right?
Right.
Okay. And did you measure the overhead of this scheduler?
We're still like this is more like a position paper. We're still working on to achieve this like a system, and then doing some measurement later.
So in my understanding, this hyperscheduler is you let the user to write some rules to trigger the preemption.
Yeah, the policy.
Yeah, to trigger. So it seems similar to the user-defined user-level scheduler. So there are some people like in Syrup in 2021 in SSP. It basically it provide an interface for user to define any customized scheduling policies.
Mhm.
So what is the difference between your work and this user-defined policy?
So which paper is that?
Syrup. It's user-defined scheduling across all stack.
So from my understanding, those like a user-defined policy only define the policy. For example, for example, it might be only targeting header line blocking that prioritize handling some other requests.
Yeah, but it can also use for preemption. So they can just add one interface to say, I only enable preemption at some point and disable.
Yeah, if they also allow the user to define what the preemption actually does, it's the similar idea.
Yeah, so,
But in most cases, I've seen some papers in those like a user level scheduling or introduce preemption into the cooperative environment. They basically let the user define a policy, like how to preempt task. There's no definition, like there's no space for the user to define the preemption task.
I see.
Yeah.
So basically, they are mostly focused on policy, which one to run first. And for your hyper scheduling, you basically want to define when to enable the preemption.
Yeah, we can also define the same policy. For example, you only care about existing tasks. You are not going to introduce new tasks in the preemption. You can just say like this request comes in, I prioritize that request. Yeah, at some level, they can be equivalent.
What's the benefit for like deciding enable the preemption instead of just design a better policy?
Because better policy is more targeting existing tasks, right? But here you give more flexibility to user to leverage this preemption to do whatever they want.
Like, can you name one scenario preemption is better than the policy? For this example, I can just lower the priority for this application and let others to run. It's similar to the preemption.
Yeah, but you can do a little bit more thing here. For example, after I can do this for example, add the user to the log list, or do some other profiling inside this preemption action. So like if you're using a policy, you only decide how to schedule existing work, right?
Yes.
And in this case, you can basically do whatever you want. Not whatever you want, but something you want, like avoid the execution or modify some states the policy owns.
Can we just abort the execution in the middle? I mean, preemption is different with aborting the execution.
Yeah, so I'm saying is that when you have different policies, you can, for example, prioritize this execution over that execution. But here, you can also abort the execution, and of course, you need to have some like a error handling code here after you have this policy. But the point here is that in the preemption, you can do many actions you want instead of like saying, I need to run this first and that first as a policy.
Okay. Yeah.
Are the hybrid execution definitions for the entire microservice for a specific function? Like what granularity can you use?
It's basically for one particular service, one application. Like by application, I mean a process running something.